So we have said a second order ordinary differential equation is said to be homogeneous when it is in the form A d squared over dx squared plus b dy over dx plus cy is equals to 0, isn't it? Where a, b, c are constant. So the first method of solving a second order ordinary differential equation is the method of undetermined coefficients, or the d operator method, isn't it? So in the d operator method, we will say where we have d dx, we are going to substitute with the d. That implies when you square both sides, you are going to get d squared over dx squared will be d squared. So you go back to your homogeneous ordinary differential equation, and anywhere you have your d dx, you substitute with d, where you have d squared over dx squared, you get d squared. Are we together? So from there we are now going to have a d squared over dx squared is d, then you can see it is d of y, isn't it? Are we together? It is d of y, meaning you are differentiating with respect to x, y twice, and this d squared over dx squared is what is d squared, so it is d squared, it is d squared y, isn't it? Are we together? It is d squared y. So from there, we now have the next one is plus b into d over dx is dy, isn't it?
Yes.
bd y, then it is plus c, cy is equals to 0. Are we together? So the first method is to get rid of the derivatives by substituting them with the d operator. So from there, we now want to solve this equation because the d operator is involving derivatives. Now we want to let this d operator to be m. Now we want to let this d to be m, so that we no longer, because we know these derivatives, isn't it? But now that we don't want to deal with derivatives, we want to solve a quadratic equation, then we let this d to be m. So the moment you let d to be m, then d squared will be m squared, isn't it? So we now have a m squared y plus b my, because d, where this d you put m, isn't it? Plus cy is equals to 0. So from here, you can see y is a common factor. You can factorize out a common factor, isn't it? So if you factorize out y, you are going to remain with am squared plus bm plus c is equals to 0, isn't it? So what is the implication here? This is a product of two equations or two factors giving you 0. Then it implies either the first factor is 0 or the second factor is 0. So this simply implies that either y is 0 or am squared plus bm plus c is equals to 0. Are we together? So you see, when y is equals to 0, it means our second order ODE does not exist. Are you seeing that? When y is 0, it means this homogeneous second order ODE does not exist. Are we together? So when y is 0, it means the second order ordinary, homogeneous ordinary differential equation is undefined, isn't it? It doesn't exist. So we are remaining with am squared plus bm plus c to be equals to 0. Now this equation we are getting is now what we call the auxiliary equation. Now this is what we term as the auxiliary equation. So it is the auxiliary equation that we are going to use to solve a second order homogeneous ordinary differential equation, the auxiliary equation. So we have found that the auxiliary equation is we found the auxiliary equation is am squared plus bm plus c is equals to 0. Are we together there? So from here, the solution, this is a quadratic equation, isn't it? So if this is a quadratic equation, then it implies m will be what? M will be formed by quadratic formula minus b plus or minus square root of b squared minus 4ac over 2a, isn't it? So that will give you the solution of m. the solution of M will be a quadratic. How to solve a quadratic equation, isn't it? Now you can see in our second order non-homogeneous ODE why we were differentiating y with respect to x, meaning x is the independent variable, isn't it? Y is the dependent variable, so it means y is a function of x, isn't it? So if y is a function of x, it means the final solution is going to be y to be equal to some function of x, isn't it? Are we together? Now from here, there are now different kinds of solutions. So if you find the solution of this, Roman 1, if you find the solution of M to be one real number, then what is your solution of the second order homogeneous ODE? If it is one real number, means when you solve this, you are ending up with maybe N is equals to minus B plus or minus square root of 0, meaning what you found inside A is 0, isn't it? Maybe over 2. So if you look at this, you find that the answer is just one. There is just one solution for a quadratic equation, isn't it? If it is just one solution, it is like a case whereby you add maybe x plus 1 squared to be equals to 0, isn't it? See, this is quadratic, but a perfect square, isn't it? So in that manner means if you solve this, you just get x to be a single solution, isn't it? You get x to be a single solution. So if you get the solution to be one real number, then the solution, because our function here, y, we are differentiating y with respect to x, so it means our y is a function of x. So the solution is going to be y to be equal to some function of x, isn't it? So that function of x is going to be a constant a plus bx. Then exponential, your solution. Are we together? So if the solution, this one real number, which is the solution, if it is just m1, then it is going to be exponential m1 x. Exponential m1, thank you. Exponential m1 x. So if the solution of m is only one real number, then this is the general solution of the second order homogeneous ODE. Are we together there? The second scenario, when you have two real numbers. What about when there are two real numbers? Meaning you found the solution to be m1 and m2, isn't it? So when there are two real numbers, then y is a function of x, like in that case we are using, then our solution is going to be y exponential, the first real number, x, then plus b exponential m2x. So it means the real number solution is defined by the exponential function. Are we together there? In case of real numbers, the solutions are defined by exponential function. Now what about if one solution is real and one solution is imaginary, isn't it? So you can end up with a case whereby one solution is real, one is imaginary. So when one solution is real and one is imaginary, what happens? Roman number 3, one real and one imaginary. One real and one imaginary solution. So maybe you add m to be equals to what? To be equals to alpha plus or minus beta j. So it means when you find the solution to be in this manner, meaning there's a real part which is alpha and there's an imaginary part which is beta, isn't it? So what is going to be there? The general solution of your second order homogeneous ODE. What is going to be the solution of your second order homogeneous ODE? So if you have one real and one imaginary, then y is simply going to be what? It's going to be cos of the imaginary. Imaginary is beta, isn't it? So it is going to be cos beta x plus sin beta x. Then your coefficient, of course, a cos beta x, and your constants, coefficients here, isn't it? And b sin beta x, then exponential alpha x. So you can see alpha was the real part of this solution, isn't it? And all the real solutions are always exponential. Are we together? So you can see the real part alpha is Exponential alpha x, because x is, y is a function of x. X is the independent variable. Are we together there? So that is when you have one real and one imaginary. The imaginary is using the trigonometric functions. Are we together? The imaginary are using the trigonometric function, and the real are using the exponential function. And remember, those exponential functions are hyperbolic functions, because hyperbolic function, according to the other equation, if you have exponential x is cos x plus sinh x, isn't it? So that means these real parts, when the solution is reached, they are always hyperbolic. But now, when they are hyperbolic, we are dealing with them in terms of an exponential function. Are you seeing that? And when they are imaginary, we are dealing with them in terms of trigonometric function, because you know very well that exponential jx is cos x plus j sin x. Meaning, when you are dealing with a case of imaginary, we don't express exponential function to have the imaginary j. We now leave them in form of trigonometric functions. Are we together? So the last solution, when Roman 4, when you have only imaginary, isn't it? Only imaginary solution. Remember, when it is imaginary will always be 1, isn't it? Because you will get the solution of n to be plus or minus beta j, meaning it is negative and positive beta j. It doesn't matter how many beta you found, the beta is what we are interested in, isn't it? Are we together? So it means the solution of your second order homogeneous ODE will be given by A cos beta x plus B sin beta x. So you've seen these are all the four possible solutions of homogeneous second order ordinary differential equation. Meaning, if you get two real numbers, there is a solution you expect, isn't it? When you get one real number, there's a solution you expect, isn't it? When you get a real number and imaginary number, there's a solution you expect, isn't it? When you get only imaginary number, there's a solution you get, isn't it? And all these solutions are from the auxiliary equation, which is resulting from the D operator, isn't it? So that is what we refer to as the method of undetermined coefficients, or the D operator method. Example number 1.